Stoichiometry is a complicated sounding word, but if we break it down, we see that it isn't too bad. The first part, stoichio, is from the Greek word for element. The second part, metry, is from the Greek word for measurement. So stoichiometry is about measuring elements. And ultimately, what you're going to see, it's about balancing chemical equations. To give a very simple example, imagine that we take one atom of element A and one atom of element B. And imagine further that these two atoms react and form the diatomic molecule AB. What we have said in words is a chemical equation. We started with one A and one B as reactants, and we ended up producing one molecule that contained A and B. So neither A nor B was lost, and importantly, we didn't end up with any extra A's or extra B's. This description is consistent with the law of conservation of matter, which, as you learned, states that matter is neither created nor destroyed during the course of a chemical reaction. So I hope you're starting to see that stoichiometry is essentially a tool that we can use to help us organize chemical information and express chemical reactions in meaningful ways that are consistent with the laws of nature. As you proceed in your study of this unit, you will notice that fairly soon we change our description of chemical reactions from one atom of element A combines with one atom of element B to 1 mole of A combines with 1 mole of B. So why are we changing our description, and what is a mole? We change our description because atoms and molecules are so incredibly small that we have resorted to measuring their masses as a means of counting or helping us keep track of how many atoms and molecules we have. As far as a mole is simply a number. It's a pretty large number. It's about 6.022 times 10 to the 23rd. And we can connect this concept with something from an everyday experience where someone might walk into a room holding a box and saying, "Hey, I have a dozen donuts in this box." Immediately, you would know that that person has a box that contains 12 donuts because you know that 1 dozen equals 12. Similarly, I could hold up a sample of water and say, this sample of water has a mole of water molecules. And so you could say to yourself, that sample must contain about 6.022 times 10 to the 23rd molecules of water. Now you might be wondering to yourself, what size container would I need to hold a mole of water molecules? To help you think about this, we're going to imagine that we take a beaker, a 25 milliliter beaker, and we place that beaker on an electronic balance. We zero out the balance, and then we add water to the beaker until the balance reads 18 grams. When we do this, we can say we have a mole of water molecules. So 18 grams of water is equal to about a mole of water molecules. Now, why this is so is one of the important things you're going to be learning as you study this unit. But to get you started in thinking about this, we're going to introduce another concept, and that concept is the atomic mass unit. Now, by international agreement, a carbon-12 atom has an atomic mass of 12 atomic mass units. A carbon-12 atom is a particular type of carbon. It's what we call an isotope of carbon. It's the most abundant isotope of carbon. It has 6 protons and 6 neutrons. Now, because 1 gram is equal to 6.022 times 10 to the 23rd atomic mass units, it follows that 12 grams of carbon-12 atoms is equal to 1 mole of carbon-12 atoms. If we look at a periodic table, however, we'll notice that the atomic mass of carbon is listed as 12.011 atomic mass units instead of 12.000. So why is that? The reason why is because not all naturally occurring carbon atoms are the carbon-12 isotope. Some, about 1%, are the carbon-13 isotope, where we have 6 protons and 7 neutrons. So the atomic mass of carbon is a weighted average. It reflects the isotopic abundance of carbon that we find in nature. This line of reasoning also holds for the other elements in the periodic table. For our final example in our introduction to this unit, we're going to think about concentration. In particular, we're going to think about molar concentration. Now, molar concentration implies moles per liter. To illustrate, we can add potassium chloride to water and create a potassium chloride solution. If we have a 2 molar potassium chloride solution, that means that in 1 liter, it would contain 2 moles of dissolved potassium chloride. Now, we can use that concentrated solution of potassium chloride to make other solutions that are less concentrated. We call those other solutions working solutions. We use an equation to help us figure out how much of the concentrated stock solution we should use. That equation is M1V1 is equal to M2V2. So this practical example is our final introduction to the major topic of this next unit, stoichiometry.